Okay, so today uh, I will show you how to implement trapezoidal rule using MATLAB, and after that I will show how to implement bisection method through C++. So first, what is a trapezoidal rule? So trapezoidal rule states that a definite integral is evaluated through this formula. So the formula, which is width of interval times 1/2 of the first and last ordinate, first plus last ordinate, plus the sum of the remaining ordinate. So the question is how to compute the width of interval. So this formula here is the formula for calculating the width of interval, wherein this variable stands for the upper limit of the integral minus the lower limit of the integral divided by the number of intervals. So, to be clear, let us solve a given problem. So, this integral, we will solve it through MATLAB using conventional integration and the trapezoidal rule. So, first, we will solve it using conventional integration. So, in MATLAB, you must first encode the Sims syntax so that your variables will be recognized by MATLAB, because the x variable, especially x, is not recognized by MATLAB unless you type Sims. So if we encode this problem, y equals 2 over square root of x, and so the syntax for evaluating definite integrals of in MATLAB is the dependent variable, which is y, then the lower limit of the integral, then the higher limit. So we'll give you this answer: 4 square root of 3 minus 4. So in decimal form, it is equal to 2.928. Next, we will implement the trapezoidal rule. It says in the problem that we will evaluate this integral using trapezoidal method with 4 intervals. So how will we do it? So the width of interval is given by this formula, which gives the answer of 1/2. So this is the table of values for the trapezoidal method, and this is the uh, answer through trapezoidal method with 4 intervals. So we will implement it using MATLAB. So by the way, this one is equivalent to this way of encoding in of x is equivalent to this one. This is the lower limit of the integral. This is the width of interval we computed, and then this is the higher limit or the upper limit of the integral. So it's just the uh, way of MATLAB for to recognize these values of x from 1 to 3 with increments of 1/2. So, by the way, this dot here is encoded because uh, we are dividing a scalar by an array, which is given by x with from 1 to 3 with increments of 1 half. So the function for or the syntax for evaluating definite integrals through trapezoidal method in MATLAB is given by traps. So the important thing here is to when using traps function, you must uh, type first the independent variable before the dependent variable, such as this one. So if we have it 2.947, so 2.9447. So in 4 decimal places, it is the answer. In 3 decimal, so that's it. So if we try to evaluate the integral using trapezoidal method with 8 intervals, so we will have x is equal to 1. So this is the formula for width of interval with 8 intervals. So as we can see, the answer from trapezoidal method with 8 intervals is closer to what we obtained from the conventional evaluation of definite integral or conventional integration. So our conclusion here is that the greater the number of intervals, the closer the answer to the one obtained from conventional integration. So next problem, so we have uh, integral of t squared with limits from 0 to 9. So first we will solve it with conventional integration. So I included GH here so that uh, I don't have to type it. I will type it in the later problem. So we have Q equal to T squared. So this is the problem we are trying to solve. And the second problem. So first we will solve it using conventional integration. Again, type first the lower before the higher limit. So we will solve it using uh, trapezoidal method with 18 intervals. 18 intervals first, then uh, we will try 21 intervals after. So first, you type the independent variable, which is t. So we have limits from 0 up to By the way, uh, if we use the formula for calculating the width of interval with limits of 0 to 9, so the formula will give us the width of interval as 1 half because 9 over 18 is equal to 0. So first, we are solving for trapezoidal method with 18 intervals. So important thing in using the trapezoidal method in MATLAB, you must first uh, type the independent variable before the dependent variable. Otherwise, you will get a wrong answer. So if I type here 2PQ, so we have an answer of 243.375. So next, we will try to implement trapezoidal method in MATLAB through 21 intervals. So this the formula for width of interval will give us interval of 0 to 3 over 7. So Q P dot squared. So trapezoidal method with 21 intervals. So as we can see, the greater the number of intervals, uh, the closer the answer of trapezoidal method compared to the answer obtained from conventional integration. So last problem for trapezoidal method. So we have integral of 2 over 1 plus g squared with limits from 0 to 1. So first again, we will solve it using conventional integration. So h equals to 2 over. By the way, the semicolon is uh, placed after this so that it suppresses the printing of this function. So using conventional integration, so the answer is pi over 2. So if we consider the decimal form of pi over 2, it's approximately equal to 1.57 correct to two decimal places. So today we will uh, evaluate it using trapezoidal method with 8 intervals. So take note that in this problem I use uh, g instead of x as variable so that uh, it will not substitute the values of x I used earlier. So if we calculate the limits, the width of interval, so the width of interval will be equal to 1 over 8. We type g equal to 0, 1 over 8, 1. So again, this one is the MATLAB's representation of tables like this for the values of the independent variable. Okay, so as you can see, it's almost the same as the decimal form of this answer obtained from the conventional integration method. So the conclusion is that uh, the more intervals for you use for trapezoidal method, the more accurate results you can get, and the closer the answer is uh, compared to the answers obtained from conventional integration. So that's it for trapezoidal method. And now we will proceed to the bisection method. So for the bisection method, so we use C++ compiler, which is Embarcadero Dev C++ version 6.3. So I have here a program that calculates, that implements bisection method with 5 iterations. So in C++, so defining a function of x, or defining a problem, or inputting a problem to be solved through bisection method is like this. So it's the same thing as x cubed plus 5x squared plus 7x minus 20. So it's the way of C++ to express polynomials with, so this one here is equivalent to x cubed, then this one here is 5x squared, then 7x, then 20. So here we have double xp, double xn, double previous x new and x new, double fxp, fxn, and fx new. So they are, meaning their values can be uh, decimal, with decimal points or floating numbers. I mean, they can have decimal places. So what we have here, int count equals 5, meaning, so we have 5 iterations to start with. So by the way, this problem is a sample problem with maximum of 5 iterations. So we have here input xn and xp, because in bisection method, you need an xn and xp to calculate x new. So this one here the while count greater than or equal to 1. So it will continue to run until it reaches the set number of iterations. Unless this condition is met. If x new is equal to x new, then the iteration will stop as stated in the bisection method. Or this one, this one. So this one here states that if fx new is greater than 0, then x new will be equal to xp. Else, uh, if fx new will be less than 0, then xn will be equal to x new. Then return. So to run this program, we will click compile and run. So just wait for it. So here in the CMD prompt, we will input a initial values of 1 and 2, meaning they are the initial values for our program. If we press enter, so these are the answers for the 5 iterations. This one here, xn, fxn, uh, xp, fxp, x new, and fx new. Just like this, as discussed in the handout. So it continues to iterate until 5 iterations as stated in the program. So again, so another problem we will solve using bisection method is this one. X to the fourth plus 10x cubed minus 4021 x squared plus 56,800x plus 292,000. So, sorry. So, by the way, before I solve this problem, I will use MATLAB's root extraction function to compare the answers obtained from this program. So first we will run it 1, 2. So here, this is the xn, fxn, uh, xp, fxp, x new, and fx new. So this program continues until 5 iterations. So first, second, third, fourth, and fifth. So the final x new is 1.28125. So we will see and we will compare it uh, with the root extraction function of MATLAB. So p equal to 1, 7. By the way, MATLAB represents polynomials in this way. If there is a zero coefficient, let's say we have here x cubed, then 5x, you insert 0 here because MATLAB represents polynomials in descending order. So if we have, so in this case, we have x cubed plus 5x squared plus 7x minus 20. So there's no need to insert 0 here because the polynomial that we will evaluate will have complete uh, coefficients from x cubed down to x raised to 0, which is represented by negative 20. So if we evaluate the roots, so as you can see, there are two complex conjugate roots, and we are only considering the real number roots with no imaginary parts. So 1.31 and 1.3125. So we can increase the number of iterations up to 10. For example, let's say 10 iterations. If we compile it, so 1 and 2. So there you have. So it's quite close to MATLAB's answer. Okay, so for the next problem, so we will solve it. This one, x to the fourth plus 10x cubed plus minus 4021 x squared plus 56,800x plus 292,000 using this compiler. So again, in representing variables raised to exponents, so this is the syntax when using C++. Pow, parenthesis x, comma 4. So in this Excel worksheet, so here are the roots that we obtained. So first we will use values of 47 and 48 for xn and xp respectively. But first, we will change the number of iterations from approximately 50. Then first, you must compile first before executing. Because if you run it without compiling, then this one will recognize the previous problem that we solved and therefore give wrong results. So compile and run. So if we use 47, 48 as initial values for x and xp, so 47 iterations, 50 iterations, I mean, sorry. So we have here, so we can consider this for 57.0179 as first root. So next, like like this one. So next root, we will have uh, 21 and 20 as xn and xp respectively. So again, we will run it 21, 20. So what we have 20.9778. So this one 20.9778. Then next we will have what's next? So -5 and -4 for xn and xp. So first, when typing initial values, we first write the xn. This is to assume that uh, a negative value will appear first. So as we can see, five, 4. So as we can see here, these are the initial values, xn and xp. Then these are the tables, xn, fxn, xp, fxt, xnew, and fxnew. So in comparison, they are quite close. The problem is it's not, this one is not correct up to 10 decimal places, only 3. So this CMD prompt follows the formatting we use in our Excel worksheet. XN, FXN, XP, FXP, XNew, then FXNew. So we have our root here as -4.009. So almost close. And for the last root, so we will have -73 and -74 respectively. So this one should have been this one, 73, -73.984. So if we run it again, -73, -74. Oh, sorry. I mean, okay. So as we can see here, so we can see that this again, this CMD prompt follows the table arrangement of xn, fxn, xp, fxp, xnew, and fxnew. So Again, we will compare it with the root uh, extraction function of MATLAB. We have here p, is another variable, p equals, so 1, 10, 4021, 6800, 292, so we obtained uh, same results as our Excel, and the program we use in C++ compiler. So thank you, and that's all for our video. Thank you for listening.